Well, we're on to another unit. This time it'll be functions and their graphs. Now that we've seen how to graph a few things, I think you'll find this a very interesting section. We'll learn about the key idea of function, which is one of the most important ideas of mathematics, and then we'll learn how to graph functions in various ways, and then at the end we'll do a number of problems that are real-world problems. You might in the past have called them word problems. But these are real-world problems that actually allow you to construct functions and their graphs and see how they apply. On that note, we'll go on. Functions and their graphs. All right, the very first thing, of course, is that we need to define what functions are. Function is really the central idea of mathematics. Took a long time to develop, but we finally have it, and we can use it in all of the material that we're going to use for the rest of the course. So on that note, let's start talking about what a function is. All right, the function idea. Well, first of all, let me make a little note here that function is being used in a technical sense. That is to say, I am going to define what function means in mathematics. Now, function means a great deal of things in normal everyday language, and some of those actually apply to what we talk about. But there will be a technical definition that I'm about to give you. Okay, first of all, I will give you what I might call two visions of function, two ways to view the same idea. Here is one way, and either one of them is fine. If you put both of them together, then you get a better sense of what a function actually is. The first way is as a correspondence. I'll need to explain this with examples. Don't worry, those are coming up. But a correspondence between two sets. And the two sets will be given special names also. So that's one way to think of a function. Another way, I'll put an or here. Another way that is also fruitful and gives you a different viewpoint is to think of a function as a machine. Again, I'll need to define what that means. A machine with input, things going in, and output, things that come out. Now, with these two ideas, you can put together, I hope, in your own mind, what a function is. So let's start with the first one, a correspondence between two sets, and then we'll go on to the second one afterwards. So the first one, number one, is function as correspondence. Sometimes this is referred to as a one-to-one correspondence, but a one-to-one correspondence really has a specific meaning that I'm not going to be using here. So I want to be careful and just use the generic word correspondence. And here's the basic idea. Imagine that you have a set, and for no good reason, let's just call it set X over here on the left. And here it is, it's some set of real numbers. Now the sets we look at in this course, of course, are real numbers, except for certain cases when we'll look at complex numbers, and those will be a little later. And let us suppose that you have a second set, a set that we'll call Y. And it's over here somewhere. Okay? Now in the set X, there are various values. Okay, let's suppose there's an infinite number, because those are the kinds of sets we'll be looking at. And over here in Y, there are also values, probably an infinite number. And what the function is actually a correspondence that says, say, this point is related to this point. So this is the correspondence here for this point and this point. So they become a pair, they are linked. We'll have to explain exactly what the linkage is, but you can see that we can develop a correspondence where each point here is associated with some point, perhaps in the other set. And this would continue until all of the points over here are associated with points over there. Now again, remember, both of these sets are all real numbers. That, remember, is our symbol for real numbers. We're talking about real numbers and only real numbers for the time being. Okay, I need to be a little more specific here. There are some things that need to be carefully defined. When we're thinking of a function as a correspondent, imagine that you're over here living in set X, and that you want to get on an airplane, say, or a car, and you want to travel over to the other set. Now, the correspondence is such that it is always the same, so that if you get into this airplane or car on one day, you will travel to this point. If you get into it on another day, you will travel to the same point. It was always the same thing. The function, the correspondence is always identically the same. Now, of course, it makes sense and is possible that two people over here, person there and a person there, might end up going to the same place. So there might be an arrow that, let me pick another arrow I haven't used. This arrow goes to here, and from this point over here, this person could also go to the same destination. Now there's nothing that makes there's no difficulty with that. Two people can go to the same destination. What you don't want to happen is that one person on different days, at different times, would go, the correspondence would send it to a different point. All right, now that's a bit vague. Let's go ahead and write down specifically what I mean by that. So this is the first version of the definition of a function. This will be the correspondence version. A function, and of course once I get writing I'll start abbreviating function as I abbreviate everything else, but for now I'll write it out. A function is, in this vision, a correspondence from the set X into the set Y. Okay, those will have specific names later. That, what does this correspondence do? It associates with each point in the X set, with each, and let's say little x's live in big X. So little x lives in big X. So with each little x in big X, some, and this is a very important word now, unique, some unique y in big Y. Okay? So every point here in the X set is associated with, if you like, every X over here goes by airplane or correspondence to a unique destination Y in big Y. Okay? So there's only one place it goes to. It's unique. So another way to see that is with the arrows that I had on the other page. This means the following situation is okay. That if you have two of these elements that live in the X set, say call them X1 and X2 to distinguish them, it is possible that they can both go to the same element Y in the Y set. That's okay. What is not okay is the other arrangement, where you have a single X, say X1 again, going to two different Y values, where these are not the same. This cannot happen if you have a function. We want function to mean this, or going to one and this one going to another one, but never this. And of course, we don't want X1 to go to 3 places or 4 or any of that. So another way that people often say this is many to 1, and this would be 1 to many. So many to 1 is okay, but 1 to many is not. Okay, so let me repeat a bit of that and write some of that down, so you'll have that in front of you. Again, putting this in words, each x, each little x, and you heard me use this terminology, people do say this, goes to, or corresponds to, or is associated with. Each x goes to only one y. Okay? Another way to say that, as I said before, is there's no ambiguity about the destination. If you think of it in terms of planes or trains or cars. All right? So there's no ambiguity about the destination. Now that's a nice colloquial way of saying this. Now let me give you a specific example. Here's an example. Here is the function I want to look at. Now we haven't got function notation yet, so you'll have to bear with me if you already know it. We want the function that takes little x's, and I'll use just an arrow like this, and it takes it to squares. Okay? So every little x is taken to the corresponding square. So the set of all the little x's that are allowed in would be the big X set, and the set of all the squares that come out of that would be the big Y set. So big X in this case can be, if I allow it to be as big as possible, it can be anything, because I can start with anything and I can square any real number. So imagine this is my set of real numbers over here. And then over here, my big Y, well, based on my own experience, squares can only be 0 or positive. They can never be negative. So I know that Y, if it's allowed to be as big as possible, would be 0 to infinity. It would include everything possibly out to infinity. All right, here's a symbol for that. Now, the correspondence is via x squared. So let me take some specific numbers over here. Here's a number, minus 2. Now it's going to correspond to what? Well, it's going to correspond to 4. Why? Because the correspondence here is square. Take minus 2, square it, and you get 4. Now notice in this case, because of the nature of this function, 2 has the same destination, because 2 squared is also 4. And then you can put in other numbers. 1/3, of course, would go to 1/9, because minus 1/3 would go to 1/9. Minus 1/3 squared is 1/9. A 0 would go to itself, because 0 is equal to 0 squared, and etc. There's an infinite number of real numbers here, and there'll be an infinite number of elements over there. So there's an example of a particular function. And what really is happening is that this correspondence sort of lives here in the arrows. The arrows are the correspondence. If you imagine your hand going in here and gripping this, say for example in this picture, this is the gripping hand picture of a function. Okay? This is a function as correspondence. The function as correspondence. It's like a big hand that grips this, and you give that fist a name. Another way to look at that might be this. The function is this correspondence. We've grabbed it all together in this ring. And in fact, this is a specific function. This is a function that I've marked with a question mark because it's a function we won't cover in algebra. But 0 under this function goes to 0. Pi goes to minus 1. Pi over 6 goes to 1/2. 2 goes to approximately 0.909. And then there's an infinite number of real numbers that can go in and that will come out. Now some of you out there may be able to guess what this function is, but don't worry about it. The important thing is that you have an idea that a function is a correspondence of some kind between here and here, as long as each value on the left is always going to go to the same value on the right. In fact, if you put those values together, a final note on the correspondence version here, a function as correspondence, which is what we've been looking at in all those pictures, with more examples to come, yields a table. Now you must have seen tables before. We'll set up this table as follows. Here on the left will be set big X. Here on the right will be set big Y. And what will be the line in between? That will represent the function. Let's do the x squared function again. So we'll put in, say, minus 2, and of course we get out 4. Now we have a table with numbers on either side. We put in 1, we get out 1. We put in that minus 1/3, we get 1/9. Let's put in pi for fun. We'll get out pi squared, and then an infinite number of numbers on either side. So what happens with thinking of a function as a correspondent is you can think of it as a table. In other words, if you know where the number begins, here as minus 2, and you know the end result, and you know that for every number in here, then you know the function, because you know it by what it does. Even if you didn't have the formula x squared, if you had all of these numbers and all of those numbers and you had them paired like this, you would know what the function is. Now that's going to have bearing when we start wondering about how to graph a function. So let's go on to our second vision of functions, the machine version. 2. Function as machine. All right, function as machine. Well, this gives me a chance to draw my standard machine for a function. It's going to be very generic now. All I need for my machine to have is an input place and an output place. So I'll even give it a little 3D for you. All right, there's my function. Let me jazz it up here with a little third dimension. There we go. I'm having fun here. All right, there's a little third dimension. Okay. This is the function, okay? This is the function, whatever the function is, as a machine. And what goes in over here? this is where the input comes from. And the whole set of input elements would be the input set, and they will go into the function. What will come out? The output set. The output set will come out and form the output set. Input set, output set, function in the middle. Now you can see how this is related to the correspondence idea. The function as machine simply says the correspondence is now going to be considered a process. All right? You can put that down if you like. Instead of being a static correspondence where you have the input set and the output set paired as in that table, you can now think of it as a moving thing. The input elements go in, the function acts upon them and produces the output. So we have this machine version of the definition. This can be very pleasant. I'll show you some examples later. So let me write out the definition. I wrote out a definition before. Let me write it out again. This time we'll call it the alternate definition of a function. And here's how it goes. Try and make it sound similar to the other one. A function is a machine in this incarnation that associates with each, and this time we'll call them input elements. With each input element, I'm abbreviating element right there with ELT, some unique, see this should sound just like the other one, so that associates with each input element some unique output element. Now previously we called those the little x value out of big X and the little y value out of big Y. But now I'm calling them input and output because that makes more sense in the machine context. Again, there's no ambiguity. Each input, x value if you like, always has the same output. The same output. Doesn't matter when you do it, you will always have the same output. There is no ambiguity. That is what makes a function. See, with a machine it seems even more sensible because when you put something in, you expect the same thing to come out time after time after time. You don't expect to put something in and to get out something one time and something else another time. So each input always has the same output. So let's go ahead and look at the example we looked at before. So as before, we looked at the function that took x to x squared. Okay, we don't have any standard notation for that yet. We will. But that's the function that squares things. Now in this machine version, there's the standard machine again. Okay, I just need room for input and output. Now the function in here is the square function. And actually, you know, writing x squared seems like the right thing to do, but I think there's a better way to do this. I'm going to write, instead of this, I'm going to write box squared. And you'll see why later. I'm just going to write it's a thing squared. Now here are all the things coming in. -2 is going to go in here. 1/3 will go in here. 0 will go in here. And say 5 will go in here. And of course there's an infinite number of numbers that can go in there. What will come out of the machine? Well, this is the square machine. The -2 goes into the box, gets squared, and comes out as 4. The 1/3 goes in to the box, gets squared, and comes out as 1/9. The 0 goes into the box, gets squared, and comes out as itself, 0. The 5 goes into the box, gets squared, and comes out as 25, 5 squared. And of course, the infinite number of numbers going in will result in an infinite number of numbers coming out. So there's one way to visualize this function. Again, this side over here is the input side, and this side over here is the output side. Okay? Now, using this machine imagery, I'm going to go ahead and give you what I like to call a sampler of functions. Now, some of these functions we will cover later in this course. There's one of them that we won't cover in this course at all, but you'll see if you go on and take something like calculus. All right. Now, this is a function that's rather strange. It's unlike the function x squared, say, that we looked at before. This is a function that's in pieces. All right? This is a function in pieces. And my pens seem to be drying out on me here, so bear with me as I switch pens. All right, a function that's in pieces. Now, here's how I'm going to define it. I'm going to say that this function gives me minus x for x's that are less than or equal to 0. Let's say it gives me 5, always 5, for x's that are greater than 0 and less than 2. And let's say it gives me something more complicated like x squared minus 1 for x's that are greater than or equal to 2. So let me encase this in the machine image that I had before. And let's see what it does to a few numbers. Now we're going to see functions like this, but we can look at them even now. Say minus 2, 1, 3 halves, and one more, say 3. And of course there's an infinite number of numbers that can go in. Let's see what happens. Minus 2. Now that is a number that is less than or equal to 0. So for numbers that are less than or equal to 0, we take minus the number. Minus 2 negated becomes 2. 1, we look in here, and where does 1 live? 1 lives between 0 and 2. So for numbers that are between 0 and 2, the output is always 5. It doesn't matter what the number is. So that one gives me 5. What about 3 halves? Well, 3 halves also lives between 0 and 2. So again, the output is 5. So there are 2 numbers that go to the same place under this function, which is okay as far as our definition goes. And finally, 3, let's see, 3 is bigger than or equal to 2. So 3 has to be, the output of 3 is what it results from squaring 3, which is 9, and subtracting 1. And from that we get 8. So there's an example of a function. We will explore these kinds of functions later, but I think you see that I've got the machine here clearly defined, and the numbers that go in, we can tell exactly what's going to happen to them as they come out. Of course, it would be much harder if I didn't tell you what the function was. We won't do that. Not for now, anyway. All right, here's another one. Now, this is a function that we will discuss later in this course. 5 to the x power. So let's take a few numbers into that, just to see how this whole correspondence or machine version of the function might look. Okay, so I'm picking a few numbers here. Let's put 0 in. 0 goes into the position of x. Then 5 to the 0, of course, you know, is 1. So 0 is associated with 1 by this function. Minus 2 goes into here. That's 5 to the minus 2 power. Now, if you remember what that is, that's 1 over 5 squared, which, of course, is 1/25. So minus 2 is associated with 1/25 under this function. Pi goes in and becomes 5 to the pi. Now, what that equals, we don't have a clue at this point. But that's what happens when that domain element, that element on the left, goes in for x. 3 going in for 5 becomes 5 cubed. And of course, 5 cubed is 125. And then we continue. So there's another example of a function. It's a fairly standard function, and we will see it later in this course. Then there are lots of functions that will remain undefined within this course. For example, trigonometric functions, because that's part of a trigonometry course. But here's a function I wanted to show you that I think you'll follow, and it really is an extension of algebra. But you don't get to see these things unless you take Calculus 2, of all things. And here is the function I'm going to put in here. 1 plus x squared plus x cubed plus ... all the way out to infinity. Now, there's not too much we can do with this at this point, but we can evaluate this for a few numbers, and I'll be using information that I have that you don't have. But I want you to see that functions come in different forms. We've seen ones that were broken up into pieces. We've seen ones that were a single formula. We saw one that was an exponentiation, 5 to the x, and now we see one that looks like a polynomial that goes on forever. Now this actually has an official name. This is referred to as a series. And you do study this, as I said, in calculus 2. Now let's see where these numbers go. If we put 1 in here, I think even you can see that 1 plus 1 plus 1 plus 1, etc., is going to go to what we must call undefined. Because adding up an infinite number of 1s is not going to yield a real number. The only numbers that we deal with now are real. So whatever this is undefined for us. You should also be able to see that when I put a 0 in, everything with an x in it goes to 0. And you're left with 1. So there's another one we can do without too much trouble. Now, putting in a 1/2 or a -3/10, if you had a little more knowledge, you would see that 1/2 will go to 2, and -3/10 will go to 10/13, etc. Now, these two numbers on the left go to these two numbers on the right, because I happen to know something about this series that you don't. But the point is, this is a legitimate function, even though it doesn't look like other functions you've seen before. All right, I think we've looked at the pictures of functions enough. We're going to stop now, and then when we come back, we'll look at language and notation of functions. The language and notation of functions. All right. Under the language of notation of functions, I wanted to mention a couple of things up front. These are just pieces of advice. There are many versions of the names, let's say, of functions, of the sets involved with functions, of the correspondences. There are many of them. Get used to them. The function notation has developed over centuries, and so there are many different versions that all mean similar things, and you just have to get used to them because you never know which one's going to turn up in practice. Also, the notation is new to you, so practice it, and practice it now while we're doing this section, because if you don't, you'll find yourself falling back into patterns of older notation that looks like this notation, and you'll be wrong in those cases. So, let's go back to how we define functions. We had, on the one hand, a set on the left that we called big X temporarily, a set on the right that we called big Y, and in the middle is where the function was, represented as a correspondence or as a machine. And now, under each of these, let me draw lines. Under each of these, I'm going to give you the standard terminology. Each of these sets has a name. The function, as in its various incarnations, will have different names. So let me start with the basic ones. The set on the left, the input set, is called the domain of the function. That is the traditional name. The output set is called the range of the function. So those are the two standard names for the things going in and the things coming out of a function. Now the function itself can be denoted in many different ways. It can be noted with single letters or abbreviations. Now that covers most of what we'll need to look at. There are other ways to indicate functions, and I'll show you that in a moment. What else can we use as terminology from the left to the right? Now the domain, let me rewrite this so that you'll have on paper what I said. This is the input set, and the range is the output set. What would elements within the domain be called, and what would elements within the range be called? Well, you might think they're called domain elements and range elements, and certainly they are, but there are other names that are also used, again, because of history. So, the elements, let's start with the domain. Of course, as I said, they can be called domain elements, and I'll abbreviate element here, domain elements. They are also referred to as independent variable. Now, this is in a context from the theory of equations, and that's where we have variables x and y, and one of them is independent, one of them is dependent. The value that goes into the function we will refer to as the independent variable. And sometimes the value that goes into the function is called the argument. Okay, that's a bit of an older piece of terminology, but it's also used. It is the argument of the function. Then let's go over here and look at elements within the range set. Now, of course, as I said, they can be called range elements, which you might expect. And the variable that comes out is referred to as the dependent variable. Dependent. Now that makes sense when you think about it, because it depends on what the independent variable was. The independent variable goes into the function and produces the dependent variable. Then, the elements that come out are often referred to as the image elements. The image under the function, the x value goes into the function and produces an image. Or sometimes they're referred to as the value of the function. The value of the function. So an x goes into the function, and then the function produces the value, which we can call the image, we can call the dependent variable, or the range element. All of these pieces of terminology for elements in the range are used, just as all of these are used for elements in the domain. All right. Well, those are the words that are used. And now we really see from this picture that a function is in three parts. So let me write that down, and then we'll come back and we'll look at these three parts again and start writing down some of the notation that's used. All right, so a function, and this is one thing that you want to keep in mind, a function consists of three parts. Now, students tend to forget this. They tend to think it only consists of one part. Let me show you what the three parts are. First part is a domain. And remember, that's the input set. Why did I write that down? The input set. The things upon which the function is allowed to act. It is also consisting of a correspondence. Or, if you like, machine. What the function actually does. And finally, a range, which is the output set. Output set. Now, as I said, students tend to only look at the middle part and talk about the function as though it were simply a machine or a correspondence. But the fact is, the correspondence of the machine doesn't have any meaning without a domain set to act upon and without the results of that action. So a function really does consist of three different things, and the more you keep that in mind, the better it will be for you. Okay. All right, now let me go back to that three-way picture that I had before. So I had over here, now I'm going to just call it domain. And in the middle I had function. And on the right I had range. And let me divide it in three again. And now let's talk about the notation that's used for this. Not just the words that are used, the language, but the notation. Domain elements are often just listed by single variables. There are some traditional ones that we will see very often in this course. Of course, x is one. T is another one that we'll see fairly often because T often stands for time in problems where time makes a difference. Let me go ahead then and go to the function. How do we notate or write down functions? Well, as I said before, we use single letters or abbreviations. What do I mean by that? Well, a function might be denoted by F, or G, or H, or any of a number of other letters, depending on the context. If you're doing a problem in which the function you're looking at is an area function, you might want to call it the function A. So you pick a letter that's appropriate. But when we're doing things in a generic manner, we'll just use letters like these. Also, there are some functions that have specific names. The natural log function, which is abbreviated by ln. Log function, which usually means log base 10, but can mean other logs. exp, which means the natural exponential function. sin, which you may have encountered in your life, which stands for the sine function. Or cos, which stands for the cosine function, etc. There are lots and lots of familiar three-letter or two-letter abbreviations or more that are used to indicate functions. But of course, you can use any abbreviation that you like. Ranges. What do the range elements look like? Well, I'm going to talk about this in more detail on the next page. But I'll list a few things here so you'll see what we're talking about. The function here has to apply to the domain element to produce the range element. The range element, it would be best if we had a notation that told us what the function was and what it acted upon. Sort of a history of where the range element came from. Well, here's the notation we're going to use, and it'll require a little more explanation. But I'll write it down. Suppose I use f here for the function, and let me use x here for the domain element. Then the range element would be written as f of x. This is pronounced f of x. It's also sometimes pronounced f at x. The notation is designed to give you that history I spoke of. It tells you the function and what the function acted upon. So you have a representation of the range element, whatever the range element is, and that tells you where it came from and how it got there. What about some of these other functions here? Well, you might have sine of x, or you might have log of x. I hope you're beginning to see a pattern here. You might have ln of x, you might have exp of x, you might have cosine of x. Now there's a pattern there. The three letters are going with a pair of parentheses in each case, or the two letters in this case. Up here, the single letter with the pair of parentheses. That's worth separating out. So I'm going to do that right now. That new range notation is new enough. That new range notation is new enough that it needs a bit of description. One thing I want to point out is, note, f of x is not multiplication. Now, when you've seen parentheses before in this course, and f like this, you might have thought this is the letter f times the letter x, in which case the parentheses really seem to be superfluous. But this is not multiplication. What this is, the actual correct notation would be f of blank. These are the parts that go together. The letter that names the function, or the triple of letters if it's log or exponent, etc., and the two parentheses. They're all part of one thing. It'd be nice if they were all kind of linked together, but they're not. So you have to think of them that way. And then what goes in here, I'll put a box here to indicate it, is the domain element goes in there. Okay? And this is not f times anything. It's f of something. So when we write this, example here, we write something like this, you will see. You might see f of x equals, say, 6 minus x over x plus 2. Now that's what you're seeing. Now how do you read this? You want to understand what this means. X is the domain element. The argument, the independent variable, all the same words, all the same object, different words. What is coming out here, of course, this is the range element. Or if you like, the image of x under f. And f, of course, is the function. So we have the function, the domain element, and the range element. The range element is written with this notation. You know, a better way to write this so that you see the process and don't get caught up on the letter here, x, is to rewrite this as f of box equals 6 minus box over box plus 2. Now this makes this look a lot more like a machine. It's a machine into which you put numbers and out of which you get this, where the number that you put in, 6 minus that number over that number plus 2, yields an output. So I'm going to use the boxes whenever I can so that you don't get confused with the letters. The box will really indicate the function. Okay, this is a way of describing the function. So, if you want to think of a function, think of this notation. Okay? F with its two parentheses. And I've put little dots to indicate that they're linked. The two parentheses are linked. Okay, what goes in here? This is where the domain element goes. Okay, but the function itself is the larger notation. I hope that image stays with you. It's really big, isn't it? Okay, let me go ahead and show you now another example, and I'll use that function notation, and I'll write it out as a machine, because we just talked about it that way. I'll use a different machine for the sake of variety. So here's a machine. Okay, now this time why don't I use the letter T just to be different? T is the input. What will be the output? I don't know because I haven't indicated what the machine is. The machine function. Let us say it is going to be called g of box, generic name, and what will it be? It will be box squared minus 2 times box plus 5. So that is what this machine actually does. It'll take t in, do this to it, and produce, well, let's see. It'll produce t squared minus 2t plus 5. So t goes in, t squared minus 2t plus 5 comes out, and this is the function in between that generates that, and this end result now is naturally called g of t. The t has been put in the box, and we have g of t. So that's how this notation works. And if you keep these pictures in mind, you'll probably be better off as time goes on. Let me bring that other one back. Remember, big F, parentheses. I just like this picture. Okay. Now, there's terminology used throughout. And let me rewrite that previous function. I put g of box down. G of box as box squared minus 2 times box plus 5. The fact is, in practice, you're not going to see boxes. What you'll see is particular letters. You might see g of x equals x squared minus 2x plus 5. Or you might see g of t is t squared minus 2t plus 5. Or you might see g of u. I hope you're catching on to this. G minus 2u plus 5, dot, dot, dot. All of these letters don't matter. They're placeholders. They're what we call previously dummy variables. That's why I like using the box. Placeholder. What letter you use is irrelevant. What matters is the structure of the function, and it is identical in each case. Okay. Some other pieces of terminology. Sometimes we say, in quotes, the function f. Okay? People will say that. Or sometimes they'll write or say the function y equals f of x. So there's a couple of things going on here. They're saying it is the function f applied to x, and that's the range element, but for short, I like to call this y, because that's going to remind me of the y values that occur when you graph points, the xy values you recall. So very often you'll see the function written as y equals f of x, and the y is a shorthand for the full version of the f of x. So let me put that down, shorthand. Now you'll see more of this later when we start talking about graphs. Okay. For example, that leads me to another piece of terminology. I can use what I have. Sometimes we know a function explicitly. Explicitly. That means we actually know how to compute it. For example, y equals 3x squared plus 4. If I say, how do I compute this for x equal 5? Well, I know that I square 5, multiply it by 3, and add 4. I have an explicit description of the function. Other times, and again we'll see more of this later, I'm just introducing the terminology. Other times, a function, say y, is only given implicitly. Now, as you go on in mathematics, you'll see more and more of these. Implicitly. For example, maybe given, I have an example here, something like this. x squared minus xy plus y cubed equals 2. Now you say that looks like an equation. Yes, it is an equation. But if I were to solve this for y, I would get it into a form like it is up here, and I could think of it, thinking of the y and the right-hand side as some function of x, I could rewrite it this way, in which case f of x would be given explicitly. However, in this one, although you can solve for y, if you think about it for a moment, you realize that it involves solving a cubic in y. When a function is given implicitly, it may be very hard. It may be hard or even impossible to write such a function explicitly. So you sort of have to be grateful for what you have. It's an implicit representation of a function. It is not explicit, but I wanted to point out the difference in those two words and the fact that that terminology is used. All right, one last picture. There's my function again. F, 2 parentheses. Could be g, could be ln, could be sin, could be exp. But the point is, it goes with the 2 parentheses, right? It's all tied together, sewed together, if you will, with these dots. And in here goes the domain element. And on that note, we'll stop and move on to the next bullet. Now let's talk a little bit more about domains. More on domains. The first thing I want to say is that let's make an agreement, you and I. We will agree that whenever a function is given to us, a function that may have no specification, we will assume that the domain is as large as it possibly can be. So let me write that down. Unless specified, because sometimes you'll have a function where the domain will be specified by the circumstances, we agree, okay, you and I will agree that the domain, as I just said, the domain of the given function is the largest set, here's the way we'll say this, the largest set in the real numbers for which, well, let's see, the largest set for which the function makes sense, for which the function is defined, for which f of x, the range elements that come out of this, are real numbers. Because right now we're only dealing with real numbers. And you can put in there makes sense, if you like. So let's see if that reads all right. Unless specified, we agree that the domain of the given function is the largest set in the real numbers, for which f of x, I guess we need to make that singular, don't we, is a real number, okay? For which f of x is a real number, or in other words, makes sense. Okay, that's the first note about domains that I wanted to pass on. And let me show you what I mean by that by giving you an example. Here's a simple example. Suppose the function, and it's often going to be given just this way, f of x equal 1 over x. Now you're probably going to want to think about that as f of box is 1 over box so that you don't get confused by the letter. But f of x equal 1 over x, say, is the given function. And nothing else is said. So the assumption is, the agreement is, that we will assume that the x's that are allowed into the f, in other words, the domain of the function, will be all the x's which make the range make sense, make it a real number. Now you can see from the range there's only one number that will not be allowed. That will be the x equals 0 number. So we agree that the domain of f is all real numbers except x equals 0. Now, you know, after writing all of that down, we certainly know what the domain of this function is, the domain that we are assuming is is the largest possible. Except that it took me a lot of words to write that down, didn't it? It would be nice if I had a notation that could make all of this a lot simpler. Say the domain of f. We ought to have a notation to say that. And then I'd like to be able to say all real numbers except x equals 0 in a more compact fashion. So I think I'll go ahead and introduce something like that to you right now. And we'll call that point 2 here. I had point 1, let's call this point 2. We're continuing with more on domains. Point 2, a shorthand notation for the domain of f, for the phrase the domain of f is DOM of f, or sometimes it's just DOM, and people write it that way with DOMF. Now I will use that from time to time because it's helpful. It's certainly short, and I think everyone understands what it means. It means the domain set that goes along with the function f. So it's simply useful, okay? And just for the record, the range is indicated by RAN of f. Now we're going to spend much less time calculating ranges. I marked that down just for completeness. Okay, the third point under domains. We'd like a compact way to specify domains, because previously I just wrote it out. Now we actually do have some compact notations. We have the notations for intervals, so like intervals, say, and you remember the notation for intervals. An example of that might be the open interval from -3 to 1, or maybe the interval that's closed at 4 and goes off to infinity, etc. Now that's a nice compact notation. But what if your domain is not just an interval? What if it's a combination of intervals, or is it some other set of numbers? What we need is we create something that I left out of the basics part of this course because we didn't need it until now. We create what we'll call set builder notation. Set builder notation. It's a way of constructing a set that is generic. It will be used here for domains, occasionally for ranges, and for other things later on. So it's good to introduce it. And what I'll do is I'll introduce it via an example. Suppose I want to take this set, which I have to write out first because I don't have the notation yet. The set of all real numbers, or all reals, say, greater than 5, or less than or equal to, say, -3. Now that is a set that, if you think about it for a moment, the numbers greater than 5 and those less than or equal to -3 are not in a single interval. In fact, there are two intervals involved here. So this set I will denote as follows, and I'll explain the notation as I go. The set will be indicated by putting curly brackets at each end. Those are also called braces. But we'll go ahead and put one at each end. And then the set will be, first thing I will write down, and the letter here again is arbitrary, the numbers x in the real numbers, where this little epsilon is the Greek letter E. It stands for element of. So we can read this as is an element of. So x is an element of the real numbers. This vertical line is read such that, and what it is, of course, is a vertical bar, if you like. We have a vertical bar. So we want a set of all the real numbers x in the real numbers such that what? Such that these conditions are met. We can write those down as saying x must be greater than 5, or, write the word or in there, x is less than or equal to -3. So there is my fairly compact notation for the sentence up here in English. And as these sentences to describe domains become more complicated, you'll begin to appreciate this notation. It is also completely standard in mathematics. So let me read it again. This is the set of all x's in the real numbers such that So here we're describing the kinds of numbers involved, and the such that gives us the condition, the actual description in this case. X greater than 5 or x less than or equal to minus 3. So if x is in either one of these intervals, then x is in this set, which I tried to describe above. So as we use this notation, let me go ahead and show you how it would work. Example, the domain of the function 1 over x can be written as the set of all the real numbers such that x is not equal to 0. Now that's the example we had before. This is the function f of x equals 1 over x that we had up there a moment ago. So I'm using that notation, the shorthand. The domain of 1 over x is this set, the set of real numbers such that x isn't 0. So everything that is not 0 can be put into this function. All right, let me show you another one. The domain of the function square root of x, another familiar function, is the set of all the x's in the real numbers such that, now what's the condition here? To take the square root, or in fact any even root of a number, the number inside must not be negative. So x in the real numbers such that x is either 0 or positive, we can say x is greater than or equal to 0. Now this one turns out to be a single interval, so we can actually write it in interval notation, which is even more compact. But you see, this works in all of these cases. Okay. Well, these two examples actually point out a couple of good points about what's usually missing in a domain. So let's go ahead and indicate what that is. What's usually missing from a domain, from a potential domain, I guess I should say. Of course, the real numbers is the largest possible potential domain. What would usually be missing? Well, where division by 0 might occur. Now that was that, as in that case for the function 1 over x. We have to throw the points out, the x values out that would make that division by 0 occur. In that case, it's simply x equals 0. Another possibility is where even roots of negatives or negative numbers, real numbers of course for us, negative numbers might occur. Okay, because those are undefined, they lead to complex numbers, and complex numbers are not what we are dealing with so far in this course. And also, just as a generic final statement, wherever the function's definition forbids. Now there are functions that actually forbid certain numbers because of the way these functions are defined. For example, a later example, which we'll talk about in the course, is the function natural log of x. And natural log of x is undefined by definition for x less than or equal to 0. In fact, the only way to define it for those numbers is to move on into the complex numbers. So there are functions that are actually, by their very definition, undefined for certain possible numbers. But usually, the kind of things you will see is you want to avoid division by 0 or even roots of negative numbers. So let me give you a couple of examples to show you how this kind of works in practice. Example, find the domain is the question. And the function here, given again in that standard form, g of x is 3x over x squared minus 4. All right, the solution is to find the domain. What I want to avoid are the things that were mentioned in my previous list. In this one, there are no roots involved, so I can ignore that. Also, there's nothing mentioned about the definition of the function. So the only thing I see that might be a problem is that I have a division, and I do not want the bottom here, the denominator, ever to be 0. So, to eliminate division by 0, what do we need? And see, this is a good pattern for you to develop. What do you need? You need x squared minus 4 not to be 0. Well, you need to solve this little inequality. It's not too hard to solve. One thing that will help is if you notice that the left-hand side is the difference of two squares. And if you remember how to factor that, this is x minus 2 times x plus 2 not equal to 0. Well, the only way this product can be 0 is if either one of these is 0. And that would be x equal 2 here or x equal minus 2 here. So we need that x is not equal to 2 or minus 2. So with that in mind, I can write down the domain of this function, the domain of g, is the set of all the x's in the real numbers such that x is not equal to 2 or minus 2. And there you go. I've just found the domain of this function. But you see the reasoning I used here? I looked at this and said, what could go wrong? Division by 0 could go wrong. I do not want the bottom to be 0, so I write that down. Half the battle here is writing this down. Once you've got it written down, then it's just an equation, or in this case, an inequality to solve. And I don't think you'll have any difficulty doing that. Let me show you another example, one that is similar, certainly in style. Find the domain. And remember why we're finding domains after all. We're finding domains because they are one of the three parts that make up a function. The correspondence or the rule is certainly something we'd like to have. The domain probably is the next essential thing. Here's the function in this case. Let's use h of x for a change. Square root of 3 minus x. The solution to finding the domain. Well, again, I look at this and I ask myself, what are the possible things that could go wrong? There's no division here, so I don't have to worry about division by 0. But I do have an even root, a square root, root 2. And so I do not want the inside ever to be negative. So, to avoid a square root of a negative number, which, as you know, leads us to a complex number, we need, and again I'm writing this down, notice the pattern here, we need what? We need that 3 minus x is greater than or equal to 0, but not less than 0. It is either equal to 0, which is fine, or greater than, which is positive. Well, this is easy to solve. We could just add x to both sides. We have 3 greater than or equal to x. In other words, reading it the other way, x is less than or equal to 3. So, if that is satisfied, then numbers in here, remember if x is less than or equal to 3, the worst that can happen is 0. Otherwise, you're taking a number away from 3 that's smaller than 3, which will leave a positive number. In those cases, this function will be defined. So, here, the domain of h is the set of all x in the real numbers such that x is less than or equal to 3. And again, this is one of those cases where I can rewrite this as an interval, including 3 from minus infinity to 3. And that interval notation that we saw a long time ago is certainly coming in handy now. Okay, we've looked at the domains of a couple of functions. Let me make some final notes here. Final notes. Note number 1. You might wonder why I'm concentrating on domains and not saying very much about ranges. Well, ranges are often harder to calculate. Okay, so we'll mostly discuss domains. Because really, if you know the domain and you know the correspondence or the machine that the function is, then together you can then construct the range. So very often ranges are really much harder and not really of much use in most of what we do. So we'll mostly discuss domains. Now, these notes, the next two notes, are technical notes. This is a tech note. This is regarding your graphing calculator. There are two things you need to be aware of. One is, when you see a key on the graphing calculator that looks like this, range, it means often window. Now, window is the terminology I will use in the course, and most of the modern calculators use window. But sometimes you'll find an older calculator that will say range, and what they mean by that is the window for the graphing screen. So it does not mean range. often means window, not the range of a function. Okay, so just be aware when you see that, it's not the range that you think it is. And the final note here is actually a pleasant one. Some familiar functions appear on keys. I won't list every possible case, but let me show you some of the ones that I know you'll see. You'll see a key that looks like x squared. Of course, this is the function f of x equals x squared. You'll see a key that has the square root symbol. That is going to be the function f of x equals square root of x. You'll see a key that will be either x to the minus 1 perhaps, or 1 slash x, or 1 over x. That, of course, is the function f of x equals 1 over x. There are other functions, but a lot of them are trig functions, or log functions, for example, or exponential functions, which we haven't talked about yet. So I wanted to leave you with a couple of notes there on some of the functions that you find in your graphing calculator. And when we come back from this, we'll practice some of this function notation. Now, the notation of functions is so new that we're going to take a little time now to practice some of it so that you can get some of those older habits about multiplication out of your system. So now we'll look at function notation practice. And I'll do this largely by example, a couple of notes here and there. My first example, I'll start out with this function. Let's let f of x equal, and I've looked at this function previously, 6 minus x over x plus 2. Nice, simple, rational function. Now, let me make a note here off to the side. Recall, this x is, in the notation of a function, okay, is a placeholder. Okay? And the other word for that was dummy variable. So, it might even be better to write this without variables at all, as f of box equals 6 minus box over box plus 2. Now you'll see why I write it that way. I want to do some calculations with this. So let me go ahead and do some calculations. I may have to bring that picture back. Let us now ask the question, what is f of 1? Now remember, this is not multiplication. This is the f function. Remember the f function, f, right? F with the parentheses all goes together. F of 1. Well, what was that function? F of box equals 6 minus box over box plus 2. Now I'm filling the box with 1. So I will have 6 minus 1 over 1 plus 2. Okay, and of course when you do these, it's automatic to simplify them. You should make that a habit. So this becomes 5 over 3, and we'll just stop there. So f at 1 is 5/3. The domain element is 1. The range element is 5/3. Let's compute another one. F of minus 1/2. Again, here's the function. F of box is 6 minus box over box plus 2. The box is now filled. This box right here is now filled by minus 1/2. Now, when you deal with negatives, be sure and use parentheses to be careful. So 6 minus 1/2, notice I'm using parentheses to be careful, and on the bottom, minus 1/2, again parentheses, plus 2. And of course, you can simplify that in whichever way makes you happy. This is 6 plus 1/2 on the top. 6 can be thought of as 12 halves, so that's 13 halves on the top. The bottom is minus 1/2 and 2. 2 can be thought of as 4 halves. Minus 1/2 is 3 halves. And then if you remember your division of rationals that we did much earlier in the course, 13 halves over 3 halves leaves you with 13 over 3. So f of minus 1/2, the function from the previous page, equals 13/3. Again, the domain element is minus 1/2. The range element is 13/3. Careful use of parentheses here and here. Please note that and do it in practice yourself. Now let's look at another one that's a little different. F of the quantity a plus h. So the quantity in here has gotten more complicated. It's not a single number like these were. In fact, it's two numbers added together in letter form. Well, if I remember the function, let me bring it back again. F of box is 6 minus box over box plus 2. I am filling the box with a more complicated object, but it doesn't matter. That object will go there, there, and there. So f of a plus h will be 6 minus the quantity a plus h, again being careful with my parentheses, over a plus h plus 2. Now in this case, there's no more simplification I can do. There's nothing that's going to cancel. So I'm going to leave it just the way it is. Finally, let me do one more with this same function, just to show you some of the pitfalls here. F of 1 over x minus 1. What will that be? Again, here's the function. I'm replacing the box by 1 over x minus 1 in all three places. So I will now have a fraction over here that will be 6 minus 1 over x minus 1, and then 1 over x minus 1 down here, plus 2. And again, you can simplify this in any way that makes you feel good. I'm just going to get a common denominator on the top and the bottom. X minus 1 is common to the top, so I will have a fraction on the top with x minus 1 in the denominator. I will have 6 times x minus 1 minus 1. And on the bottom, a similar fraction. This is not the only way to simplify this. This is just one way for practice. 1 plus 2 times x minus 1. Of course, when you flip and multiply, the x minus 1s will cancel each other. And then I will have, multiplying out the top here, 6x. Then I have minus 6 minus 1 is minus 7. All over 1 plus 2x, put the 2x first. Then I have 1 minus 2, so I have minus 1. Okay? The domain element, the range element. And actually, this was the range element. I could have stopped there. From here on, this is simplification. Always wise to do for the sake of argument, but remember, the answer is really done at this point. All right, let's look at another function so we can get this pattern here. Example, suppose I have a function capital G of x equals 2x squared minus 3x. Now, in order not to confuse myself, I'm going to rewrite it as G of box equals 2 times box squared minus 3 times box. Now the structure of the function here is made clear. Whatever goes in the box here goes in the box on the other side. And then you can do a series of examples. I'm going to want to make a point here, so let me do G of x plus 1. Well, G of x plus 1, remember that's what's going in the box. So I'm going to have 2 quantity x plus 1 squared, because x plus 1 goes in that box also, minus 3 times x plus 1. Again, it goes in the final box too. And then, just because I want to compare this to something I'm about to do, I'm going to multiply this out. And I'm going to leave out a step. So I'll put dot, dot, dot here. If you multiply this out, and I know you can do that, you will end up with 2x squared plus x minus 1. Okay, I'll box that in so you can see it. Now, let me do something else. This was G of the quantity x plus 1. X plus 1 went in each box. Let me now compute G of x plus G of 1. Now, some of you may suspect that those are the same. Let's see in this case what happens. G of x is easy. I just copy it from up here. And I'll put it in parentheses just to be careful or safe. 2x squared minus 3x. Just copied that. Plus G of 1. Now, G of box is that. Put 1 in there. I'll have 2 times 1 squared, which is 2, minus 3 times 1, which is just minus 3. So when I simplify this, I have 2x squared minus 3x minus 1. Please note that these two are not equal. What's different? The x and the minus 3x are what's different. But they're not equal. which means that g of x plus 1 and g of x plus g of 1 are not the same. Now, that should lead you to a general conclusion. Let's write it down. In general, do not draw conclusions about this functional notation until you have actually proven it. In general, if you take f of x plus h, that's not going to be equal to f of x plus f of h. In general, the functional notation does not split up like that. Now, the reason that you might think that is because you're used to multiplication. And in multiplication, you multiply f times h plus f times x plus f times h. And that would seem reasonable. But in functional notation, that's not the same thing at all. Okay? Not the same as, let's go ahead and write it out, say, not the same as taking 4 times x plus h. Because 4 times x plus h is indeed 4 times x plus 4 times h. But this is not that. This is not multiplication. This is f of box. Remember the big picture. F of box. These all go together. This is not multiplication. All right, let's do another example of something you can do with this functional notation. Here's something that might be phrased this way. If f of x is given to you as 2x cubed plus ax squared plus 4x minus 5, and you're told that f at 2, or f of 2, is 5, the question is, what is a? What is that letter right there? Well, you have enough information to do this, and the solution is most elegantly put together this way. You have f of 2 equal 5, write it the other way. 5 equals f of 2. Now you have the function here, and although I didn't write it with boxes this time, you know that x is just a placeholder. Put 2 in wherever x is. Using this format, I then will have 2 times 2 cubed plus a times 2 squared plus 4 times 2 minus 5. Well, we can simplify that. 2 cubed is 8, so this is 16, plus 2 squared is 4, 4 times a. This is 8 minus 5, so that's plus 3. So this is 19 plus 4a. I'll put a period there. Remember this format I said we'd be using throughout the course? This is one long equation. So this 5 on the left is now equal to 19 plus 4a. Let's go ahead and write that down. 5 is 19 plus 4a. Now we can solve for a. Move the 19 over. We have minus 14 is equal to 4a. And then reversing it and dividing by 4, a is equal to minus 14 over 4. Or, because you can't help yourself, it's minus 7 over 2. So this is just another example of using this functional notation in a particular situation. How about a definition that will allow us to use it even more? Definition. Well, I'm going to define something called the difference quotient. The difference quotient. Now, if all's right with the world, it ought to involve both a difference and a quotient. The difference quotient of a function, say, just for the argument here, call it f, at a point, we'll call it a here, or at a number, don't want to call it a, we'll call it c, put in quotes. So the difference quotient of a function f at a number c, c is in the domain of f, is, this is what I mean by the difference quotient, f of x minus f of c over x minus c. Now you know that ought to ring a bell if you think back to when we talked about lines in the previous unit. We had difference of y values over difference of x values to get a slope. This looks just like that. And in fact, this is the slope of a particular line. And of course, in order for this to make sense, comma, there's one thing you need to take into account. You don't want the bottom to be 0. so you make sure that the x that you choose is not equal to c. So that's the difference quotient. It's introduced because it's easy, it's algebraic, and it also leads eventually into calculus. But for now, let's just go ahead and calculate one with a given function. Suppose f of x is given to be 2x squared minus x plus 1, and c is given to be 2. Find the difference quotient. And it was called a difference quotient well because there were two differences and a quotient. Solution? Well, I'm going to need f of c, so let's calculate f of c. F of c here is f of 2 because c is equal to 2. And here's f, again written without boxes, but by now you should be catching on that this is a placeholder, as are all these other x's. So the place now needs to be filled with 2. So 2 times 2 squared minus 2 plus 1. Well, that's easy enough. This is 2 squared is 4 times 2 is 8. 8 minus 2 is 6 plus 1 is 7. Hence, we can go ahead and write down the difference quotient, f of x minus f of 2 over x minus 2 is f of x, well, let's go ahead and substitute in, 2x squared minus x plus 1, parentheses. Always keep parentheses until you actually do the operation, in this case the subtraction, minus 7, because that's what we figured f of 2 was, over x minus 2, and I'm getting a little cramped here, so I'll move to the next page. This will continue to become 2x squared minus x minus 6 over x minus 2. And really, that is the difference quotient. You could stop there. But since we've had practice in factoring, let's go ahead and see if we can go any further just for the heck of it. The top you might try factoring as 2x times x times something. And then if you pick the right values, and it turns out plus 3 and minus 2 do it, on the bottom you have an x minus 2. Of course, now x minus 2 over x minus 2 is 1 wherever x is not equal to 2. But the difference quotient, remember, it's not here, but in the original, remember, we said that x was not equal to 2. So there was no division by 0. Well, if x is not equal to 2, then these numbers are non-zero. This over this is 1, and so you can simplify this to 2x plus 3. But I'll put that in brackets because that is a good skill to have, but it is not essential. This is, after all, the answer. Okay, we've had a little bit of practice now with the notation of functions. There's one more thing we want to look at before we start graphing these functions in earnest. We have to look at how to graph them. So the next topic will be visualizing functions, and that will be in a moment.